All right, so we'll get started. Before we start, I do want to show the schedule for the next couple of weeks. You might notice that our first midterm are going to take place in 2 weeks, so it's going to happen in class. In here, that's the written portion, and we'll also have a take-home portion that tentatively I make it due on Monday at noon the week after. But if you need alternative deadline because of other stuff going on, just let me know, okay, as soon as you can. And what it covers, the scope of it, just up to everything that we'll be able to cover by next Friday. So whatever we get get done on Friday the 18th next week, and then that will be the scope for the midterm. So I will announce specific the topics one more time once we know how much we cover. But as you can see right now, we are here. And I think we'll be able to finish this chapter, Bayesian inference for a mean, today. And we also have a lab 2 that I posted, different lab assignment, the team assignment for this time. So check the link and all that. And today we will get to do a little bit more practice of doing conjugacy derivation with a different model, and then some Monte Carlo simulation overview as well. So homework 2, which I posted last week, it is about the first chapter, Bayesian inference for proportion, so it's due next Wednesday. And then there's a homework 3, which is about Bayesian inference for a mean. This was what we're going to finish today, as well as lab 2. Both of them are about this mean chapter. So I make them both due on Wednesday, so I will be able to post solutions and then grade the lab so that you will be able to use them as your study guide, study material for the in-class version as well as the take-home. Okay, so that's the tentative plan. But I understand a lot is going on for everyone, especially have other due dates, exams and all that. So ideally, we'll all take the in-class midterm on that Friday. But if you need a different deadline for a take-home, just let me know. Okay. And again, the drop-in NRO deadline is right before the spring break starts. That's what I was hoping to take the midterm exam, everything in week 6. So in week 7, before we leave for the break, I'll be able to return the graded stuff for you. And so that's why we have a little bit, a little bit deadlines over here. But like I said, homework 2 is about the previous chapter, so you should be able to do everything about it already. Homework 3 and lab 2, what we cover finished today, you will have everything you need to do them as well. So, all right, so that's just a little bit announcement and everything. And definitely let me know, reach out if you have questions. With that, we're gonna continue our Bayesian inference for a mean chapter. For some reason, they asked me to update. Give me a second. I'll pause my recording and Zoom. And this is what we were doing on Wednesday. Just finished the last part. And we can talk about the lab 2 a little bit and then some other additional topics. All right, so I know Wednesday was pretty heavy on the derivation side. So the final result that we got is this thing. Okay, so this is, well, we're working with a normal model for a continuous outcome variable. And we are assuming that mu is the only unknown parameter. And we showed in class step by step that eventually, if you give a normal prior for the mu parameter, assuming that sigma is known, then it is a conjugate prior, meaning that you're going to arrive at equation 10 of your posterior distribution of mu to be another normal. And we talked about the mean and the standard deviation of that normal. And especially for the mean, if you remember, we discussed that it's a weighted average between the prior mean and the sample mean. Okay. So there was a question, I think, from email after class on Wednesday, what is y bar? So y bar is the average of all of the yi. Okay, so that's why n times y bar equals to sum of yi. So the data is fixed. So once you get your sequence of observations, y bar is given and fixed. So actually, there was another question, I think, last time during class as well. So if you look at all you need to know in order to update your prior from the posterior. So mu 0 and sigma 0, they're from the prior, right? And then we have this normal sampling density for the data. So we did all of the derivation, and eventually when we arrive at the posterior mean and the posterior standard deviation, you can see that we actually don't really need to know what are the observations for each, like y1 through yn, but really as long as we know the y bar or the sum of them, so I deleted just now, but m y bar equals to the sum of yi. So as you can see in practice, as long as you know the sum of the yi, then you actually know uniquely what the posterior distribution is. Okay? So this is a important concept as well. And that's why in our code, you see that we have our mu 0, sigma 0, that's from the prior. And from there, you can get phi 0, that's also the prior. And we need to know this y bar, which is coming from the data itself. We have a fixed phi, which is about that sigma. We assume that we know what it is. And then eventually you can write just very straightforward 2 lines of code to get your updated mu and updated sigma. And then you can now do what we call multi-column simulation. You can generate a large number of the draws and then try to summarize what it is in the posterior. So that's what the plot that we saw on Wednesday. And you can see, if you want, you can also plot the prior and the posterior on the same graph, like what we did before. So you can also see how it's changing from the prior combined with the data to the posterior. Okay. So this is what we covered on Wednesday. And the other half of the story is that, remember, we have mu and sigma, both are parameters in a normal model. So what we have done so far is we assume that mu is unknown and sigma is known, and we know that normal is a conjugate prior for mu. Okay? The other half of the story is, what if the other special case is that, let's suppose mu is known, so we don't need to worry about mu, but let's work with sigma. Okay? So this is the other case, like I said, that sigma is unknown and then mu is known. So mathematically, as we know from our knowledge about Bayesian inference, is that, well, sorry about the typo, it should be sigma over here. So only one parameter sigma that is working right now, because mu is already known, we don't need to worry about it. So just like before, I put it behind the conditional sign and then highlight in red. So that's the indication that you don't need to worry about the mu parameters. We're working with sigma. Okay. So the data model still stays exactly the same. Okay. From the joint density, you'll be able to come up with your likelihood function. Remember, in the past, we write mu, sorry, because back then we're working with the case that the likelihood is a function of mu. Right now, it's just going to be a function about sigma, because that's the unknown parameter that we're working with. So with that, we will, again, just like what we did before, we need a prior for the sigma, and then we'll be able to derive the posterior for sigma as well. So for the rest of this part of the lecture, I just want to show you that, well, there exists a conjugate prior for mu or for sigma as well, if that's what we want to do. And specifically, we can have a gamma conjugate prior for not sigma, but 1 over sigma squared. So this is the phi that we worked before. Okay, so you see that a lot of times with the normal results and everything, things a little bit easier to work with the precision. But all you need to know is that 1 over sigma squared, if it follows a gamma distribution, I'm going to give you the density in a second so you can get the chance to do the derivation. So 1 over sigma squared, the sigma squared is not negative, is positive because you're working with a standard deviation. So 1 over sigma squared is something positive as well. Okay? So this gamma prior distribution that we're able to give to it is a useful density specifically for a positive quantity, and we have a particular density function for it. And since we know about the concept of conjugate, so what this is saying is, well, if I start with the gamma, alpha, beta, I'll give you the density in a second. If I combine with our likelihood function, assuming that only sigma is unknown, then I should arrive at a different gamma. Okay, so that's what conjugate distribution or conjugate prior really means. So I'm going to show you the results first and then give you the chance to do the derivation. This part of the derivation is much easier than the other one that we did. The mean case was very complicated because we have to deal with that mu, and mu is almost everywhere, if you remember. Okay. For this 1 over sigma squared is slightly easier. So let me show you the gamma density that you should be working with, and then I'll give you the chance to do the derivation itself. Okay? So if I have this, if I know 1 over sigma squared follows a gamma alpha beta, what that tells me is that the prior of 1 over sigma squared, I'm not sure why, okay, it's working, yeah. So it's gonna be beta to the power of alpha, and then gamma function of alpha, and then eventually 1 over sigma squared, this whole thing, to the power of alpha minus 1, multiplies with, in the exponent, negative beta times 1 over sigma squared. Sorry about this. Let me write on the different new line, but everything is multiplying together. So I'm saying this multiplies with exponent negative beta over sigma squared. So a little bit hint and highlight before I let you to work on the details. So alpha and beta, they are the known parameters that you're going to use later. So you can consider all of this as constant one more time because they're not about sigma squared. Okay. What is important is 1 over sigma squared, the whole quantity raised to the power of alpha minus 1 times exponent negative beta times 1 over sigma squared. So these are the important terms that you need to use when you're trying to do with the Bayesian Bayes rule derivation. Of course, don't forget all of the density function that is coming from the normal. So with that, I would just say that write out the density, joint density, and then express it as alpha, sorry, as L sigma. And then from there, you should be able to go to your posterior density. So maybe instead of 1 over sigma, maybe write it out as 1 over sigma squared. So everything is going to be about the 1 over sigma squared. So the starting point, as you know, is going to be, we have all of this, and also conditional mu should be proportional to its prior and to its likelihood function. Okay. So I tell you what the prior should look like for a gamma, which is around equation 14. Equation 15 is the stuff that you need to work on a little bit to extract everything from the likelihood function only about 1 over sigma squared. And then the rest is doing this derivation. Okay, so I will pause for now, give you a few more, like 5 minutes-ish to work on the detail. And equation 16 is the final answer. Okay, so once again, as you know, you need to combine the terms from the prior and from the data likelihood, and then recognize everything about 1 over sigma squared to be another gamma. Okay.
Professor?
Yeah, go ahead.
For the normal distribution and equation 15,
yeah.
Why is the second parameter sigma? Isn't it usually sigma squared?
Yeah, good question. So I think, so the question is how we use this term in particular. So I think I mentioned it early on. There are people use different notations and everything. So we just gonna say that mu is the mean and sigma is the standard deviation.
Oh, okay. I'm used to it being the variance.
Yeah, I know. Some people will used to be the variance where like sigma is written as sigma square, but whichever is fine, they are equivalent to some degree.
Okay, great.
Yeah.
Thank you.
No worries. Yeah. So equation 15 is what we saw before. Yeah, on Wednesday we did a bunch of manipulation about equation 15 in terms of mu, but now you need to manipulate it in terms of 1 over sigma squared, which I promise is much simpler to do than the mu case. If you remember what we need to do about mu, we have to take the squares, expand the terms and everything. But with 1 over sigma squared, everything is much simpler. So I'm going to pause here and let you work on part of the derivation. Equation 16 is the final goal, and I'm sure with some exercise and all that, it will be much easier to arrive at than what we did on Wednesday. Yeah, in case people forgot about the density of the normal, here, the density of yi, I'm just going to write out 1. It's going to be 1 over 2 pi sigma squared, exp yi minus mu squared divided by sigma squared. Okay, so that's the normal density that we used before, and you need it for equation 15 as well. And the note here is that everything should be about sigma now, sigma squared, 1 over sigma squared, because mu is constant. All of the yi's are constant as well. take your time. Okay, I'm gonna try to do the first steps here. And let me get a whiteboard, okay? So we want, as we know, every time we do this Bayesian Bayes rule derivation for a continuous prior, we're gonna work with the continuous version of the Bayes rule. So from the prior, we know that this is beta to the power of alpha, and then gamma function alpha, and then it's 1 over sigma square. That's the parameter to the power of alpha minus 1, and then exp, I think negative beta times 1 over sigma square. Okay, so this is what the prior is about, and we were saying earlier that this is a constant. This is a constant, this is a constant. When we're doing the proportional sign, we don't need to worry about those two terms. Everything else is about 1 over sigma square, so we need to keep that. Okay. So the likelihood part, I will highly recommend just start writing it as a function of 1 over sigma square. That's the parameter, which we know should be the joint density of everything. You can write sigma, you can write 1 over sigma square, it doesn't matter over here. So here, as we know, there are IID. So once again, it's a joint product. Okay. So we have I from 1 to n. Okay. Within each, we know that it's 1 over square root of 2 pi sigma square. Okay. And then in the exponent, we have negative yi minus mu squared divided by sigma squared. Okay. So this is direct application of the normal density. And then let's maybe simplify that a little bit, because eventually we want to keep every term about 1 over sigma square, and anything not about it is a constant, so it can go into the proportional sign. So with this, let's see. Let me just, before doing that big product, do something a little bit more. So for example, here, I can take out this constant, I can put it aside, okay? And I had the other term to be 1 over square root of sigma square. So that becomes, because remember, my parameter is 1 over sigma square, so this will just become 1 over sigma square, the whole thing to the power of 1 over 2. Okay? Because I have 1 over sigma square, and then take the square root of that. So that is equivalent of 1 over sigma square and the whole thing to the power of 1 over 2. Okay. And then the rest, if I only focus, remember the parameter is 1 over sigma square. So I can take the whole thing as yi minus mu square, this whole thing, times 1 over sigma square. Okay. So this is everything before we take the product. So let me use a big bracket to represent that we have to take the big product, the big pi over all of them. And when that happens, so again, the pi over here about yi, okay, so everything not about yi, just the whole thing to the power of m. So I have 1 over 2 pi to the power of square root to the power of m, 1 over sigma squared to the power of m over 2. And then in the exponent, I'm simply adding up all of them, and then the whole thing times 1 over sigma squared. Yes. Oh, good catch. Sorry about that. So there should be a 2 here. Sorry. There should be a 2 here, and there should be a 2 here. Sorry about that. Okay, so maybe the best way to write it. Okay, so first of all, so good catch. So there's a 2 here. I missed it. Sorry about that. And so remember, so here we have a 2. Okay, and then because eventually we're trying to recognize things about 1 over sigma square. So I'm gonna move my 2 over here. I'm gonna move my 2 over here. Okay. But it's equivalent. That just depends on where you put it. But that's a good catch, Carl. I guess previously on the previous slide, I probably missed that too as well. So sorry about that. So that's not a constant because it's multiplying with 1 over sigma square. And so we need to keep that. But there are constants here. So this is a constant. So we can say goodbye. But everything else is about 1 over sigma square. So we need to keep them. Okay, so I think we did the steps together, right? The prior, we have some constants not to be considered. the joint density, which is the likelihood function, we also ignore some kind of the constant, but we also manage to simplify the other terms as well. So the next step and the last step for you is to combine those two. And you can see that they have very general similar structure, right? You have 1 over sigma squared raised to some power in the prior. You have 1 over sigma squared raised to some power in the data. And then you have in the exponent, some negative terms times the 1 over sigma squared in the prior. And similarly, you have something negative, and then times 1 over sigma squared. Okay, so you need to combine those terms and then trying to recognize the posterior distribution for 1 over sigma, which is another gamma because it's a conjugate prior. Okay, so I'll give you a couple of more minutes to work out the rest, and then we should be good to continue. All right, so let's do this together. And like I said, I hope you also feel that this is much easier than what we did on Wednesday, because the simplification, first of all, like the prior as well as the likelihood is easier to deal with, especially the likelihood, because in the past we have to deal with all of the square terms, right? About the y's and the mu's, but here mu is a constant, so we don't need to worry about it as much. So the posterior, 1 over. By the way, sometimes because there's so many terms to be conditional, you can just write a straight horizontal line just to represent that everything is being conditional. Okay, so let's use that simplified notation. So I just need to multiply the prior from the likelihood. Okay. And what do we have? From the prior part, or I should say, from the prior, we have 1 over sigma squared to the power of alpha minus 1. And then from the data, we also have n over 2 in the power. So in the joint, I mean, in the product, we have 1 over sigma squared to the power of alpha minus 1 plus n over 2. Okay. And then in the exponent, okay, we have from the prior negative beta. Okay. And then from the data, we have sum of the yi minus mu squared divided by 2. It's the sum of those two terms multiplied with 1 over sigma squared. Okay, so at this point, we're almost done because if you look at what we have in the last line, we have alpha, 1 over sigma. So let me use a different color. We have 1 over sigma raised to some power. And then in the exponent, we have negative something multiplies with 1 over sigma. So if you look at the prior, I know prior is a different gamma density, but it does show us a general form of the gamma density. So this alpha plus 2 over n is our new alpha in the posterior. And this beta plus the sum of yi minus mu squared divided by 2, that's my new beta in my posterior. Yes. Mm-hmm. So at this last stage, I'm just combining the terms, right? And if you agree with what we have over here, then what we have here is 1 over sigma squared raised to some power. And we know that that some power should be whatever the new alpha that we have minus 1, because that is what a gamma density looks like. Okay, so I'm saying that this alpha, so let me write it, alpha plus n over 2 is my new alpha in the posterior. And then similarly, my beta plus the sum of yi minus mu squared divided by 2. This is my new beta in the posterior. Great. So if everybody agrees with that, let me come back to the slide. And that's what equation 16 is. So equation 16 is, equation 16, as we can see here, we've got our alpha plus n over 2. Great. Okay. And we got our beta plus, so I moved the 1 over 2 a little bit, but this is what we need over here. Okay. And then just like what we did with the normal, with the mean case, with the mu, here we can use R gamma. So gamma is a very well-known, widely used distribution. So R gamma is generating random draws from a particular gamma. And then if we think about it, alpha and beta, they're from the prior, so you will give those numbers before you start. N is fixed once you know the data set, and all of the yi's are fixed, right? Once you know the data set. And the mu as we have in this particular situation, we assume that it's known. So you will have a particular numbers to work with. So you have all of this quantities known, so you will be able to use simulation-based method to simulate a large number of draws from this gamma distribution for the posterior of 1 over sigma square, and then summarize the results. Okay. So before I show you the code, which is very similar to what we did with the mu case, I know there are some questions early on about how to write out the density and everything. I will say when we're working with any kind of Bayesian inference procedure, you will see that, and you probably notice what I usually like to write. I usually have whatever for example, the prior distribution that I have, and then I directly write out what the density is in terms of this parameter. Okay? And here for the sampling density, we know, so in this particular case, we have L, which is the likelihood function over, it's a function of 1 over sigma squared, because that's the parameter, but it's equivalent to the joint density of all of the observations given mu and sigma. Okay? So it is this thing, each of this following the normal distribution. Okay, so you need to be super careful about what is the unknown that you're working with in a particular equation. But at the end of the day, the two derivations we have done so far, one for mu, the other one for 1 over sigma squared. At the end of the day, the prior should be a function about the parameter. The likelihood should be about a function about the parameter. And eventually the posterior as the product of the prior and the likelihood function should be about a function of the unknown parameter. And that's why we're happy to throw away all of the known quantities, like the data, like in this case, the mu's and everything. So we don't need to worry about them. They all go into that proportional sign. But every term related to the quantity of interest, like our 1 over sigma squared in this case, they need to stay because they are part of the derivation process. Okay, so try to see the similarity, but of course, like I said, this one is much easier to deal with, at least in my mind, because I know Wednesday we took a lot of time trying to do the steps about the normal, the prior, and everything for mean and all that. But regardless, like I said, eventually they're all conjugate. And then once you're able to get it, you will be able to do some kind of simulation-based inference eventually. And also, I should say that all of the exercises that we've been doing, albeit they can be a little bit tedious and challenging, they're all still about algebra. Okay, we're trying to find the correct terms, trying to collect the correct terms, and then trying to recognize what it is eventually. The only thing that we used calculus for is when we are trying to keep that constant in without using the proportional sign for the beta case, which is one of the homework questions. I hope you got the chance to do it in homework too. So that was the only case I think so far that we're using some practice and knowledge of doing integration instead of just little simple algebra. Okay? So see the big picture, because like I said, and we're going to do another exercise today as well. If I give you a prior density, if I give you a likelihood, you should be able to try to derive what the posterior is, given the general procedure. Of course, each model going to be different, but it's the same general idea. And then, like I said, most of the time, it's mostly just algebra. All right, so the little exercise or example that I have over here is that, well, let's give a gamma 1 prior for my 1 over sigma squared. And then I have a mu, let's just say mu is 8 given to us. And then as you can see, you need these two lines in order to get your alpha n and beta n. That's the new beta and new prior and new alpha and new beta for your posterior. And with that, you'll be able to do everything about what you need. So down here, we're doing Monte Carlo simulation. And as you can see, just to not confuse ourselves, because remember, all of the prior and posterior derivation is about 1 over sigma squared. So instead of naming it a sigma, I just call it inverse sigma squared, so I don't get confused about what I'm drawing from. Okay, so I'm drawing draws from this gamma posterior, which is about 1 over sigma squared. But if you want to do inference about sigma, you need to take the square root, right? And then all that to work it out. So with that in mind, you can, of course, do a density function of the posterior. If you want, you can put it side by side or overlaying with the prior and see how things change accordingly. Okay, okay, good. All right, so that's